Alright, a discussion of the Riemann curvature tensor concludes the mathematical preliminaries part 2 of the course, of the Riemannian geometry part of the course. Now we switch our focus to matters of physics. In particular, in this lecture, my concern is how to write down the laws of physics in the presence of gravitation. Okay, and the answer to this question is to a great extent provided by the so-called minimal coupling principle or the minimal coupling prescription. Let me start by asking this question. Suppose some physical law concerning some non-gravitational phenomena in special relativity is known. And by non-gravitational phenomena, I mean phenomena which do not involve tidal forces. Okay? Suppose we have such a phenomena which doesn't involve tidal forces, and its equations or laws, the form of the law is known in special relativity. And my question is, how do I write down the corresponding version of the law, same law, involving the same non-gravitational phenomena in general relativity? Okay? And as I said, the answer to this, to a great extent, is provided by the minimal coupling principle. Let me state it. The minimal coupling principle states that in the physical laws in Minkowski space, one needs to make the following replacements to obtain the version of the same law in general relativity. First, replace the Minkowski metric by the closed space metric. Second, replace the partial derivative by the covariant derivative corresponding to the Levi-Civita connection. And in case in your mathematical expression of the law you have a Minkowski volume element, replace the Minkowski volume element by the diffeomorphism invariant volume form or the general coordinate invariant volume element, which is given by this square root of minus g times dnx. Okay, this is the volume form. dnx is the simple volume form, and if you multiply by the square root of g, you get the invariant volume form. So if you make these replacements, in the law in Minkowski space, automatically you get the version of the law in curved spacetime. So let me give some example to drive the message home. Let me pick a non-gravitational phenomena, for example, equation motion for the electric and magnetic field, which is Maxwell equations. So Maxwell equation, which is a non-gravitational phenomena, it is not caused by gravitational forces. And this is the version of Maxwell equation in Minkowski space or in special relativity, which is this partial derivative of f nu is equal to the source j mu. Of course, I'm just talking about the inhomogeneous Maxwell equations. We also have the homogeneous Maxwell equations, which are given by the Bianchi identity. Right now, I'm not talking about them, just the inhomogeneous Maxwell equations. Now, the minimal coupling prescription says that if you turn on a gravitational field, all you have to do is to replace the partial derivative by the covariant derivative corresponding to the Levi-Civita connection. Okay? As you can see, partial mu has been replaced by Nablus of mu. And then you get automatically the correct version in closed space-time or gravitational field. Let me give another example. This is regarding conservation laws. For example, you can look at the conservation law for the electric charge or particle number, if you remember from fluid mechanics, which is given by del mu j mu equals 0. Or if you think about the conservation of energy momentum in fluid mechanics, which is given by del mu of T mu equal to 0. But T mu is, of course, the all-important stress energy momentum tensor. Now, this equation is true in special relativity, that is in Minkowski space. And the minimal coupling principle says that in order to obtain the appropriate version of the same equations, of the same laws in the presence of gravity, all you got to do is to replace the partial derivative by the covariant derivative with the Levi-Civita connection. So you get Nablus of mu, j mu equals 0, and Nablus of mu, T mu equals 0. Alright? So that is very simple. The minimal coupling principle is used by physicists, general relativists on a daily basis to write down equations which are appropriate for closed spacetime, that is in the presence of gravitation. And now let's see why this works. So in the presence of gravity, physical laws must respect diffeomorphism invariance, general coordinate invariance. We know that. So the laws should take the same form either in Cartesian coordinate system, or spherical polar, or any other random coordinate system, some non-inertial coordinate system, anything. Okay. So that means that all physical laws must be cast in terms of tensors, which in terms of tensors in the general coordinate transformation are diffeomorphic. Okay. Now, we all know that the partial derivative is not a tensor under general coordinate transformations, but the covariant derivative is. Okay. So that's why this making the replacement by partial derivative with the replacement of the partial derivative by the covariant derivative makes sense. Okay. Also, this volume element will by itself not be general coordinate invariant, but this invariant volume form will be. Okay. So this also makes sense. Next, this minimal coupling prescription is consistent with the equivalence principle, which says that in a freely falling frame, the laws of physics will appear in the same form as they appear in special relativity. Okay. Now, in freely falling frames, let's remember that in freely falling frames, the metric will appear as Minkowski, and the connection coefficients will vanish. We know that. Of course, the tidal forces do not vanish, but as I said, that we're only considering phenomena which doesn't involve tidal forces. In that case, in a freely falling frame, we can eliminate the gravity in the sense. The metric will be replaced with the Minkowski metric, and the connection will be 0. Now, in that case, what happens is that, let's say this equation, or maybe better looking at this equation. If we go to a freely falling frame in closed space-time, the partial mu acting on any quantity will be given by del mu of the same quantity. I'm assuming that is a tensor, plus some pieces which contain the connection. Okay, as many, you'll have as many pieces containing the connection as many as the indices. As many indices are there in this object. All right. So now in the freely falling frame, these will vanish, and then you'll get the partial derivative of this. So you'll recover the laws of special relativity. So this principle is consistent with the principle of equivalence, which says that if in a gravitational field, if I switch to a freely falling frame, my equation should reduce to the equation of special relativity. And that is precisely guaranteed because when I go to a freely falling frame, this partial derivative, this covariant derivative will turn into a partial derivative. And the connected pieces will be all 0. So the principle of minimal coupling is consistent with both the principle of covariance, general coordinate invariance, and the principle of equivalence. That's why it works so nicely in general. Of course, this is only a prescription, and prescriptions can fail. We haven't derived it from first principle. Let's see what kind of situation it fails. Now, it can fail for a situation where things directly, or the physics involve a direct coupling to the Riemann tensor, that is, tidal forces. Now, one example of this is the equation of motion for the spin of a rigid body. Consider a rigid body which can spin. Now, in special relativity, the equation of motion of this would be given by the spin will be given by, let's say, d is d tau, the proper time, or some defined parameter, equal to 0. This is true in special relativity. Now, you would think, again, so this d tau I can write using t dot del, as we have done before. This equals, I'm sorry, t dot partial. But t is the velocity vector along the trajectory. Then this equals 0. The d tau can be written in terms of t dot t is nothing but dx. This is t. Alright. So if you apply the minimal coupling principle, then all you have to do is to replace this partial by the covariant derivative. And you would think that this is the equation of motion for a spin of a rigid body in the gravitational field. However, remember that a rigid body which is extended, there are tidal forces on that, and since different parts of the rigid body is experiencing different amount of tidal forces, there'll be a tidal torque which will start causing the spin to change, okay, or the spin to change. So the right hand side should not have been 0 because the spin is changing, right? Because we have tidal force. But the minimal coupling principle is not able to reproduce that phenomenon. So whenever tidal forces are involved, it is a rule that minimal coupling principle will fail, and we have seen one example. Obviously, it will fail because it cannot account for tidal forces. So it's best to use the minimal coupling principle in non-gravitational phenomena, that is phenomena which do not involve tidal forces or tidal torques. All right. Okay, so the next thing which we want to study is the status of conservation laws in the presence of gravity. Now, why do we want to revisit this? I thought you might have thought that this is a settled issue, but let's see why. There's a subtle reason. So consider the covariant conservation law in which we have replaced the partial derivative by the covariant derivative in the presence of gravity. Let's say this is the electric charge. Del mu, envelope of mu, J mu equals 0. Now if I write del mu, J mu, using the rules of covariant differentiation, we know this is going to be partial mu, J mu, plus, because this has an upper index, I have to put one connection term, which will have upper and lower index mu, and then another index nu contracted with J. Okay, so this being equal to 0 means del mu, J mu, is equal to, let me take this term in the other side, you get minus gamma mu mu nu J. So now this looks like trouble because the continuity equation has a source. So this you will remember that this is the usual continuity equation which you learned in special relativity, and now you have a source. So is the current, is the charge conserved after all? So this is the question we have to answer. So it sounds good when we replace the partial derivative by the covariant derivative because the equation becomes general coordinate invariant. But what happens to the charge? Because now we have a source term. Does this source term ruin the conservation law for the charge Q? If you remember from special relativity, which is given by the volume, spatial volume integral of J0. So the zeroth component integrated over all space gives you the charge. Is this charge still conserved even in the presence of the source term in the equation? And the answer is yes, it does. Let's see a little bit of math to see how this happens. So what I'm doing is that taking this equation and I'm integrating this equation over space-time volume, okay, not the space-time. This is 0. Let's remember that covariant conservation law means this is 0. So integral of a 0 is 0. So the left hand side, that's why I put a 0 on the left hand side because this is integration of 0. And now in the second line, I've processed the covariant derivative that I've already done once before. It gives you this. And then I'm going to use this identity, which you guys should do as a homework. If gamma mu mu nu, if you have two indices common in the gamma, one up and one low, one below, then this you can show this is equal to the derivative of square root of minus g divided by square root of minus g. All right. So if you plug this here, then you get the third line. So in the third line, the first term is of course this term, and the second term root of minus g multiplied by gamma mu mu nu, using this is equal to del nu of square root of minus g times j nu. Okay, but nu is a dummy index, so I can relabel it to nu. It doesn't matter if I convert this nu into nu. And if you look at these two terms, they combine nicely using the Leibniz rule of differentiation, right? So the first term is when the derivative acts on j mu. The second term is when the derivative acts on square root of g. So I can combine these two in a single derivative term, which is del mu of square root of minus g times j mu. And now once we have this, I can write this term in components. I can run the sum of the dummy indices. First, mu will take value 0, so del mu square root of minus g j0. And the second term is when you have the mu will run over the spatial indices I, del I, square root of minus g, ji. So this term is what I've written in the next line, and this del I ji, this I can write in the form of this usual divergence in 3-vector notation. Okay, I've written the same thing in the 3-vector notation. All right. Yes. Now this term, when I integrate over all space, this overall space, so this d4x, let me do the spatial integration first for this term, the second term. Let me do the spatial integration first. And if I do the spatial integral of a total divergence, all of you know that this will become a boundary term at infinity. Okay? And let me assume that at the boundary there are no sources. All the sources are located deep inside. So the j at the boundary vanishes. As a result, using Gauss divergence theorem, you can show that this term vanishes. No contribution from this if you assume the sources are localized inside. You can also assume that there are sources all the way up to spatial infinity. For example, if you have an infinitely long wire or infinitely long plane, but all you have to assume is that the total flux of charge coming from infinity and going to infinity are the same. Okay, so they balance out, and the net flux from the surface at infinity vanishes. If you assume that, then the second term goes to 0, and we can drop it, and then we are left with just this term. This term is the total time derivative. No, not total time derivative. It's the derivative of time. So I can do the time integration first. If I do the time integration first, then I get this conservation law. That this quantity, let me do the time integration. So d4x will be given by d3x times dt. And then you have del dot time derivative g is 0. If I do this integration of a time derivative, then of course I will get. Let me just erase this. After integration, what you'll have is g is 0 at time. Upper limit of integration, df minus g is 0, and the lower limit of integration, which is d sub I. The spatial, and this is x I'm suppressing, but they're there. Okay, and then this I'm calling each of these integrals. I'm calling the charge. Okay, so 0 equals final charge minus initial charge. That means the charge is conserved. So the difference between the charge expression in special relativity and general relativity is that you have to insert this factor of square root of minus g. Okay, this is not minimal coupling because this is not a 4-dimensional volume form. This is a 3-volume, but still, you have to insert this factor of square root of minus g, and then you can show that this is the charge in special relativity, which is conserved. Although you have a source term, we got a conservation law. All right, so even though covariant derivative of this is equal to 0 implies that. All right, now that we have seen that the covariant continuity equation for this J mu, for current density 4 vector, does indeed in general relativity lead to the existence of a conserved charge given by this expression in blue fonts, Q of t. We can ask the analogous question for energy momentum tensor, right? So we also have the covariant continuity equation for the energy momentum tensor given by the covariant divergence of the stress tensor vanishing. And our question is, does it lead to the conservation of energy momentum for vectors? As it did in special relativity. So in special relativity, recall there was this continuity equation for the stress tensor, and that immediately led to the conservation of this quantity, this vector, 4-vector conserved quantity, T superscript nu, which is given by the all space integral of T0 nu. So, our question is, does that still hold in general relativity when we have, instead of the usual continuity equation, a covariant version of that? And the answer is not so straightforward as it is for the 4-vector current density J mu. Okay? So to see why this is not so straightforward, let's try to replicate the same steps as we've done for the J mu. Okay, instead we will do this for T mu nu. So let's take the covariant continuity equation and integrate both sides over all space-time. with the invariant spacetime volume element d4x times square root of minus g. Alright? Now the answer is going to be 0 because we are integrating 0. And then the covariant, then we, just like we did previously, we will work out the covariant derivative, covariant divergence of T mu. And because T mu have two indices, there'll be two terms which have the connection in them, right? So this term, which is extra compared to what we have for J mu, I am distinguishing in red fonts, okay? In red fonts, I am indicating them so that you understand that this is the part which is different from the conservation law for J mu. Alright? So the first two terms are the usual ones which we had before. That is one which involves a partial derivative, and the other is a connection term in which mu and mu, in which the two indices of the Levi-Civita connection are contracted. And one can show, just like before, the first two terms can nicely be combined into a total derivative, so the partial mu of this quantity. However, the last term, which is in red fonts, integral of that, or does not, or not the integral of that, that cannot be written as partial derivative of something, cannot be written as a total derivative, okay? So, as a result, this term in the red fonts abstracts the construction of a conserved charge. If this term was not there, one could have happily written down an expression for the energy momentum for vector in general relativity of the, by this similar kind of an expression that we had before for the J mu, which would be square root minus g. So this is a 3-volume integral, all space integral, not all space time, just all space, and then t 0 nu. If this term in the red font was not there, we could have had a conserved quantity like this, but we see that the term is there. It is not necessarily 0. It is not a total derivative. So that means we do not get a conserved energy momentum vector just from this continuity equation. So at this point you might think, well, this is very strange, because I expected the covariant continuity equation for the stress tensor to give me energy momentum conservation, and it is, when we process the steps, it seems to be giving something the opposite. The energy momentum tensor is not conserved. Well, at this point I will remind you, in special relativity, remember Minkowski space is translation invariant in both time and in space, okay, right? Homogeneity of time is there and homogeneity of space is there, and conservation laws are tied to this homogeneity, right? Using Noether's theorem, if you have some symmetry like homogeneity of space and homogeneity of time, that leads to conservation law. So in general, when we turn on a gravitational field, the presence of the gravitational field will violate or destroy the homogeneity of space and homogeneity of time. As a result, we should not expect stress tensor, stress energy momentum tensor of matter to remain, give us some conserved quantity, because we know matter is interacting with gravity and energy is being swapped between the gravitational field and the matter. So by itself, the matter's energy momentum should not be conserved. But in one case it will be, or in some cases it will be, when there is a killing vector. Let's say the gravitational field, that is the metric or the background, has a killing vector k. We know what these are. Killing vector represents symmetries of the metric. If there is a killing vector k, then one can construct a vector current density, J mu, which is given by the contraction of the stress tensor with the killing vector, T mu, K nu. And one can show that this 4 vector, J mu, which is made out of the contraction of the stress tensor with the killing vector, also obeys the covariant continuity equation, just like electric current, just like particle number current. And we know from what we learned in the last slide that if we have this kind of a 4-vector equation, then it indeed leads to a conserved quantity. So, because of the killing vector, we are able to come up with a 4-vector J mu, 4-vector current density, and that would lead to a conserved quantity, which I have indicated in blue fonts here. So, again, integral, all space integral of root g times J0, and J0 here is T0 nu times K nu. So, Again, if you have a symmetry, then indeed things, energy or momentum would be component. In particular, if this K is time-like, it's a time-like vector. It is just like having homogeneity in time, and we will call this conserved charge to be energy. On the other hand, if K is space-like, that is, you have some kind of homogeneity in space in some direction, then that component of that charge, P, corresponding to a space-like killing vector, we will call linear momentum or momentum. Okay? So, all hope is not lost. Actually, just because the covariant continuity equation for T mu does not directly give you a conserved charge, does not mean energy momentum can never be conserved. They can be in generativity, provided you have some homogeneity of space or homogeneity in time, that is, existence of killing vectors. Okay? So that is the moral of the story. If you have killing vectors, then the covariant continuity equation for stress tensor would lead to conservation law of energy or momentum. And sometimes you can have both, like you can have multiple killing vectors. So as you know, for maximally symmetric spacetime, there will be largest number of killing vectors, and in that case, you'll have all components of linear momentum and energy conserved. All right, so that brings us to the end of our lecture, and let me summarize and provide an analysis of what we did. So, first thing we did was rate by rate, we mean acceleration of the convergence or divergence of a family of geodesics, in particular a one-parameter family of GT6. And so we took the Newtonian limit of the equation we obtained for the acceleration of geodesics, which is called the geodesic deviation equation, and we found out that the Riemann tensor, or some components of the Riemann tensor, turn into the tidal forces of Newtonian gravity. So the Riemann curvature tensor is the GR analog of tidal forces in Newton's theory. After that physical motivation, we presented the formal mathematical definition of the Riemann curvature tensor and studied its various properties, symmetry, antisymmetry, Bianchi, etc. And in particular, for the Levi-Civita connection, or for the Riemann curvature tensor derived from the Levi-Civita connection, we worked out the total number of independent components of the Riemann tensor. And this number turns out to be d squared times d squared minus 1 over 12 for d space-time dimensions. So, as I said, we are keeping our mind open and studying general space-time dimension, not just 4. Of course, for d equals 4 dimensions, so which is the case of our world, this number is equal to 20. And the Riemann tensor, remember the Riemann tensor is a 4-index object. So if there were no symmetry properties and it was completely unrestrained, then one would have d raised to the 4 components, which for 4 dimensions means 4 raised to the 4, which is a staggering 256 components. But because of this nice symmetry, antisymmetry, and Bianchi properties of the Riemann tensor, this number 256 gets reduced to 20. Okay? Alright, then we studied physics in the presence of gravitational field. In particular, we wanted to look at how do laws of physics, especially laws of physics corresponding to non-gravitational phenomena, which do not involve tidal forces, how do they look in the presence of gravitational field? And we introduced the minimal coupling prescription or minimal coupling principle, which tells you how to do that. And this is already consistent with the general coordinate invariance property of gravitation and also the principle of equivalence. And we gave a couple of examples to see how this works out. As I said, if the underlying phenomena involves tidal forces, then this minimal coupling principle will fail. But in an overwhelmingly large number of cases, this works, and it's a very useful formula, a very useful prescription, which is used day to day by general relativists. Alright, in the next lecture, we are going to introduce the equations of motion for the gravitational field of the metric sourced by the stress energy tensor of matter. Now, this is an important milestone for our course, Before that, before we write down the equations, we will discuss a couple of tensors which are derived from the Riemann curvature tensor, namely the Ricci tensor, the Ricci scalar, and the Einstein tensor. These will be important because they play an important role in the form of the equation of motion for the gravitational field. It turns out that the equation of motion for the gravitational field are expressed in terms of these tensors. So those equations of motions are called the Einstein field equations. Okay, this is an important milestone result for the course. So please pay attention to the next lecture. But with that comment, I will end the lecture here. Thanks for your attention, and I'll see you next time.